First, let's identify some key terms for black holes. A stellar black hole is a singular black hole caused by the implosion of a single star. A supermassive black hole is a black hole resulting from the collision of multiple black holes. Anything can become a black hole, it just needs to be compressed enough. This concept is known as the Schwarzschild radius. It is the point at which an object becomes so dense that its gravitational pull is great enough that not even light can escape. Gravity bends space and time, and the gravity of a black hole results in a warp that can be used to identify them. This concept is known as the gravitational lensing. A photon sphere is the point at which photons orbit the black hole and are unable to escape and unable to be sucked into the black hole.
Singularity. It's the point in the black hole at which space and time become infinitely curved and dense. It serves as a concentration of mass and gravity, giving black holes the ability to pull in light. Tidal force. Tidal force is the varied increase of the force of gravity on an object as it approaches the singularity. An event horizon is basically the point of no return. It's the point at which not even light can escape the pull of the collapse. At this point, there is a massive acceleration, one so big that mass is spaghettified. Spaghettified is the actual word used by scientists to describe the effect of the tidal force. Wormhole. Wormhole is basically moving or spinning black hole that uses the dimensionality of the universe to create a tunnel from one point to another.
For the calculations in our project, we chose to use the mass and radius of the black hole Cygnus X1. Cygnus X1, discovered in 1964 by a rocket flight, has been subject to much study, including the studies of physicist Stephen Hawking. It is located in the Cygnus galaxy, about 6,100 light years from the Earth. It is 6 million years old and is the result of a single stellar implosion.
The escape velocity of a black hole, we can use the escape velocity equation that we figured out in class. The square root of 2 times the gravitational constant times the mass of the object over the radius of the object. We chose the black hole Cygnus X1 for our calculations. Therefore, we plugged in the mass of Cygnus X1, which is 14 times the solar mass, here in our important measurements category, and 26,000 meters is the radius of this black hole. So, doing all the calculations for that, we have that the escape velocity for Cygnus X1 is 3.8 times 10 to the 8th meters per second. This 3.8 times 10 to the 8th is greater than the speed of light, which is 3.0 times 10 to the 8th meters per second. Therefore, light will not escape from Cygnus X1, making it a black hole candidate.
So we said that light will not escape from a black hole once it passes the event horizon because the photons will not exceed the escape velocity. But this doesn't answer our question. What about matter? Can't we travel faster than the speed of light? We're humans, so evolution will let us make faster stuff, right? Actually, no. There are some things that not even human ingenuity can overcome. To accelerate anything with even the slightest bit of mass to light speed would require an infinite amount of energy. This is because, as the speed increases, the matter is more massive when compared to the velocity. We touched on this theory in Lab A1. Theoretically, matter at light speed would allow for time travel, but since we have only a finite amount of energy in the universe, matter reaching light speed is impossible. There's a reason why Einstein called light speed the universe's speed limit. Even gravity does not act immediately. Yet, as in most cases when the laws of physics are applied to the universe, there are exceptions. But they are few and far between in this case. So here is the answer. In 99% of circumstances, no photon, particle, or matter can travel at a velocity fast enough to escape from a black hole once it crosses the event horizon.
Also, we called Cygnus X1 a black hole candidate. We cannot know for certain if Cygnus X1 is a confirmed black hole unless its mass falls into a precise range. The exact mass of an object so far away is exceedingly difficult to calculate. The estimate we used in this equation does fall within the 3.5 and 16 solar masses range, but this is not a 100% certain calculation. There are other astronomical events which could explain an absence of light, so that evidence is not enough on its own either. Thus, we can say that Cygnus X1 is almost certainly a black hole, and you wouldn't want to get too close if you happen to be in that part of the universe.